So what have we done? We captured a sample of animals and we've marked them. We release them back into the population. We allow them to randomly mix. Let's hope that they randomly mix, right, with unmarked individuals. And then we're capturing a second sample, and then we're going to record the number of marked and unmarked individuals in that recapture. Now notice that you probably want to capture a number of second samples, right? And then take the, what? Average, right? Giving you time to say mean all together. I can hear everybody in the class just in a chorus of everybody saying, take the average, Dr. C. So in that average of the second sample, we have the average number of individuals that are marked versus those that are unmarked. Okay? So what we're doing with this method now is that we're assuming that the ratio, I'm going to move this up here, we're assuming that the ratio of the marked individuals to the unmarked individuals in the second sample is the same as the ratio of marked individuals in the first sample to the total population. Okay? All right, because here we go. We've captured a number of individuals, and we have that number of individuals that we know that we marked. Let's say we captured 20. All right? And the total population size, or N, which is a common notation, is what we're trying to figure out. Right? And what else do we know in this proportion? We know 3 out of the 4 terms, and so we can calculate it. Let's say that the total number of individuals that we catch in the second capture is 40. Okay, so we capture 40 animals. All right, so the first time we caught 20 and marked them. The second time we've caught 40. And then we say, out of those 40, how many are marked? Right? So let's say only 10 of them are, or as many as 10 of them are marked. That might be kind of a lot, actually, right? So now what do? All right, well, we're going to cross multiply, right? We're going to take this equation that we have here, and we are going to use it in order to solve for n. Okay, so n times 10 equals 20 times 40, which is what? 800. All right, and so n is going to be 800 divided by 10, which is 80. So this tells me that my total population size is 80 goats. All right, does that make sense? So all of this depends on knowing how many that you marked to begin with and how many that you recaptured, and the number that you recaptured is then we count the number that are marked in the recapture and set up this equation. Okay, so again, this assumes that the ratio of marked individuals to unmarked in the real world is the same as the ratio of marked individuals to unmarked in our samples. Okay, so notice what will happen to these estimates if some things change. Okay, what's going to happen if you recapture a lot of marked individuals? Sometimes people use traps when they're capturing their animals, and they bait them. And you can end up with animals that we might refer to as trap happy. Okay? Trap happy, meaning that, oh, they like the traps. They keep coming back to the traps. So we're no longer sampling randomly, right? It's not random, but we might not be aware of that. So that, again, this is one of the problems with the methods. If we have animals that keep coming back, this number here is going to go up, right? Let's say that ends up being a 20 instead of a 10, okay? And then, so what's going to happen to our population size? If we're dividing this number by 20 instead of 10, our estimate of population size is going to go down, right? We're only going to have 40 individuals in our population instead of 80. By the same token, what's going to happen if some of our animals that we mark die? And this may be more frequent, actually, is that the marking technique that we've used may be somewhat harmful to the animals. We have to be careful about that. So let's say we mark some animals and they die from the marking, or they avoid being captured again because now they've learned that being captured doesn't feel so good, right? So this number here, the number of marked individuals, let's say it goes down to 5, okay? Then what's going to happen to our total population estimate here if this becomes a 5, right? This 800 is now going to be divided by 5, and then again, our total population estimate in this case is going to be too high. All right, so basically what have we said? Well, we've talked about what this ratio means, and we've talked about the fact that we're making an assumption that the animals that you've marked have randomly mixed with all of the other animals out there in the population, right? That you've got this random mixing, and that your recaptures, the ratio of individuals that are marked to the total in the recapture is going to be the same as the total number of marked individuals out there in the real world. The same ratio. Okay. So what are some other methods for quantifying population density? Well, I mentioned line transects before, but we can talk about them again, line transects and belt transects. And it's really... It's good timing that I'm doing this online because, in fact, it's the use of both line and belt transects that Dr. Strong and I use in order to estimate the abundance of some of these organisms along the coral reef that we monitor. And here's a nice picture of us underwater. You can kind of imagine us underwater while you're back here in Keene. And so what am I doing here on the right is that I'm laying a transect line, which is just a 100-meter tape measure, and just laying it across the bottom of the reef. The reef actually looks a little bit prettier than this. Our photography, since we took these pictures ourselves, are not the greatest. The visibility doesn't look so hot in these particular photographs, but it's actually not so bad. And here you can see Dr. Strong is, whoops, getting used to my iPad here. Here you can see Dr. Strong is taking some data on a clipboard. All right. So what we do is we move along the transect line, and we are counting fish. So we do actually 3 different surveys. We do a fish survey, an invertebrate survey, and a substrate survey. The fish and invertebrates all utilize this belt transect method, whereas our substrate survey utilizes a line transect method. Okay, so in order to have a belt, what we do is we have a certain amount of area alongside the line. Let me just kind of shrink this for a minute here. So if this is our 100-meter transect line, what we want to do is to estimate the number of fish that are 2.5 meters out from this line in this direction and 2.5 meters on the other side of this line. So it's really this total area here, which is going to be 5 meters in total, times our 100-meter transect line. And we actually do this in sections. So we divide the transect line into a number of sections so that we're actually sampling 4 20-meter sections, okay? And you say, well, why isn't it 5? Well, we leave some gaps between our sections, okay? We don't sample a certain amount of area in between so that our different sections can be samples along a single line. All right, and so in order to count the whole belt then, what we do is we use a rod. We usually use a piece of PVC pipe that we carry along with us, and then we can tell how far out we are. Here's a picture of some students. This is actually Dwight over here, who is a Keene State student who's since graduated. And this is another student who lives on the island of Providenciales, helping out. So you can see the PVC tube here and the fact that they're moving along the transect line slowly so as not to disturb the fish, and counting these fish that tend to be hanging out along the bottom here anyway. And we end up getting data that looks like this. So there's certain indicator species that we look for, like butterfly fishes and grunts, snappers, parrotfish, moray eels. And so these are the four different sections that we sample with the 5-meter spaces in between. And then we have numbers of individuals within each of those sections. And then we calculate the mean fish abundance for each particular type of fish down along the bottom. And graph that mean together with a measure of variation like we always need to do. This is plus or minus standard error, or SE. And so we can see that what we've come up with is a relative measure of abundance, the number of these different kinds of fish per section, right? Per 20 meter by 5 meters, right? In terms of this belt transect survey. Now when we do the line survey, the line transect, all we do is, again, we have our transect line, the same line, and we drop a weight every half meter. We use a little fishing weight to do this, and we drop it on a string so we can pick it back up again. And what we do is record where did that weight fall? What kind of substrate? Was it rock? Was it live coral? Was it dead coral? Was it sand? And we record the different substrate categories. So you can see we're actually taking samples right along the line as opposed to measuring a belt area. There are many other kinds of ways in which ecologists use sampling methods, especially for insects. Here is the use of some suction traps that can catch flying insects. You can see this big sort of vacuum cleaner kind of thing where insects get sucked in. Here we have a DVAC suction sampler. Again, it's sort of a vacuum that's going up to this backpack here to power it and sucking in insects. You can just kind of sweep this along the ground. You can see it's a little bit more powerful than the sweep nets that you've used. So a lot of different kinds of sampling techniques. Just to show you a few others, you can just directly count them. If you can see insects on leaves or branches, you could count the number of beetles per leaf or per branch. Sweep nets you know about. Aspirators are these little tools that you actually use your mouth with to suck them in. And you don't get them in your mouth because you put a filter between that, but you're using the suction of your mouth to actually vacuum the insects off of a surface. Beat nets are where you put a capture screen underneath a tree, and then you beat the tree with the net, and that causes things to fall down into your screen, and you pick them up that way. Burlese funnels are a way of getting ground insects. I'll show you that in the next slide. With a Burlese funnel, you capture a whole bunch of leaf litter and soil, bring it back to the lab, and then what you do is you set it up under these lamps, so you've got heat and light here, which these ground-dwelling insects or arthropods try to avoid. And so what they do is they kind of move down from the soil sample and end up trapped in the alcohol below. And notice that you can take several random samples of dirt and soil in different locations, so that, again, you can estimate abundances of these different kinds of arthropods in different areas based on your repeated samples. Other methods involve using mist nets for birds. You can set up these nets and birds become entangled in them. Don't worry, they usually don't get hurt. You can just untangle them and let them go again, unless you're marking them for a particular purpose. You can actually go out along the Ashwillet River Trail, and if you go off trail enough to your left, if you're coming from Keene, you'll find some mist nets that are set up there by some Antioch students. If you do go out there, don't disturb them in any way. Just want you to go ahead and take a look at them, but don't, if there are any animals, don't pick them up, don't touch them, and don't disturb the nets. But you can go out there and look at them. It's very interesting to see. Pitfall traps are basically just a way of putting a cup in a ground. Here you can see these little plastic cups. You can use metal coffee cans. And so with a pitfall trap, if you have the ground running here, you can dig a hole and put a little cup in it. and your poor little unsuspecting either mouse or beetles or other kinds of ground-dwelling arthropods can fall in. Usually you put some kind of preservative, like alcohol or ethylene glycol or something that the animals will fall in, and then you can come pick up your pitfall traps later. And then, of course, you can put a certain number of these traps out. You can sample in wider spaces. You can put them closer together. Again, depending on your total area that you're trying to sample and the estimate of relative density that you're trying to get. Sticky traps work well for aerial insects. These are basically just these yellow things here you can see covered with a sticky glue type material, and so flies and other winged kinds of insects will just fly into them and get stuck, and you can pick the traps up later. So all of these are different kinds of methods that you can use to trap organisms. I mentioned the fact that you can use baited traps to capture small mammals, and here's a picture of a baited trap down here. And again, they're depending on what your purpose is for sampling. Some of these are better and some of these are worse for actually getting accurate estimates of density.